Thanks for joining me for this video. I first want to make sure I give credit to the College Mathematics First Edition textbook by Scottsdale Community College. It is a free online resource that's available, but I did get some of the information from that textbook. So thank you for making it an open resource and sharing it. So this video is going to be about exponential growth and decay. So an exponential growth or decay function is a function that grows or shrinks at a constant percent growth rate. It has the formula given here, where A is the initial amount. So this A that's not raised to an exponent is an initial amount, and B is the growth or decay factor. So I'm just going to call it the growth factor, but it could be a decay factor. If B is greater than 1, then the function is growing. And if B is less than 1 but greater than 0, so it's still positive, it's a fraction, a proper fraction, then the function is decreasing, or it's a decay. Okay, so you can kind of see what they're telling you here is you always have 1 plus r or 1 minus r in parentheses. You'll see when we get to numbers, it's easier to tell with numbers. But the key here is your formula for an exponential function is highlighted in red, and that A is the initial amount, and B you're going to see is the growth factor. Now we've talked about another type of function. You've probably learned about a linear function, and in linear function you also had a way to express growth or decay using an original amount and an average rate of change, which is kind of like a growth factor. The linear model, you will see, has an absolute change or a constant rate of change, which is called a slope. An exponential model is going to have a growth factor or a relative change, meaning a percentage is usually is how the growth is described or the decay is described as a percentage. So let's look at some examples just to kind of see what's going on here. So here's a table. We're going to take the function in the first two rows and we're going to pick out the initial value. We're going to pick out the growth or decay, decide which one it is, and then we're going to pick out the rate, the growth rate or the decay rate. So for the first one, the initial value is always the number that's not raised to a power. So here you can see that 430 is your initial value. If you look at the next example, let's just go ahead and find the initial value. You will see that the 23 is what's in front. It's not raised to an exponent, so that's the initial value. So the initial value is always that front number that's not raised to an exponent. You're going to be able to tell if it's growth or decay based on the base, the number that is raised to the exponent. If it's larger than 1, so 1 point something, it's a growth. So this first row, the 1.15, is a growth. And that's because it's greater than 1. If you look at the second row, the 0.8, it's a 0.8. That's less than 1. So that is an indication that it is a decay. So 1 is your cutoff. If your number, your base, is greater than 1, it's a growth. If your base is less than 1, it's a decay. And then you can find the rate of growth or the rate of decay by subtracting the growth rate from 1. So you would do whatever's in the parentheses. If it's larger than 1, then just subtract 1 from it. So 1.15 minus 1 is 0.15. And then 1 minus 0.8 is 0.2. To change it to a percent, you would just multiply by 100. So the first one is growing at a rate of 15%. The second one is decaying by a rate of 20%. Okay, so now we're going to go the opposite way. They're giving us if it's a growth or decay. They're telling us the initial value, and they want us to write the function. So we always start off with function notation, f of x. Our initial value is 1.87 times a growth with 5%. So 5% as a decimal, you can divide by 100 or move the decimal over twice to the left, is 0.05. And then you add that to 1. So it will be 1.05 raised to the x. And that's it. The next one, we'll do f of x equals, the initial value is 52. We see it's a decay, that means it's going to be less than 1. So we would do 1 minus 10% as a decimal would be 0.1. So that would be 0.9. So 0.9 raised to the x. So hopefully after seeing this chart, you'll be able to fill in a chart yourself. And given a function, you'll be able to pick out the initial value, if it's a growth or decay, what the rate is, or vice versa. If you're given information, you'll be able to write a function for it. So let's look at this word problem, number 1. In the year 2008, India's population was 1.14 billion and growing at a rate of 1.34% per year. So the percent, this is giving away that it is an exponential growth because it's a change, it's a percent change. It also gives it away that they tell you to write an exponential function. But if they didn't, the percent change is what tells you that it's an exponential function and not a linear function. So write an exponential function for India's population using P of t to represent the population at time t, which is the number of years since 2008. Okay, so a couple of things. First of all, P of t is what our function is going to be. Instead of f of x, it's going to be P of t. So that's telling you that the variable you're going to see is t. Remember that your basic formula is f of x equals a times b to the x. A is the original amount. Our original population is 1.14. And then we need a growth rate or a decay rate. It's growing, so it's going to be larger than 1. 1.34 as a decimal, you can divide by 100. You will see it's 0.0134. Since it's growing, you add that to 1. So it'll be 1.0134. And instead of raising it to the x, it asked us to use the variable t, so we'll raise it to the t power. And that's it. That's how you write your exponential function. So your original amount, the 1.14, multiplied by the growth factor, and it is growing, so it was 1 plus the percentage, the growth rate, raised to the variable. And that's it. That's our function. Now for part B, use the function from part A to predict the population in 2025. So here is where you need to take into account where you started. So it's the number of years since 2008. You're in 2025. So you want to subtract 2025 minus 2008, and you get 17. So 2025 minus 2008, you get 17. So 17 is what you want to use for t. That's the number of years. So P of 17 is 1.14 times 1.0134 raised to the 17th. So put that in your calculator. And when I put that in my calculator, I got 1.43 rounded to the nearest hundredth. So this is our estimate for population. So 1.43 billion people would be our estimate.